Thank you very much for your invitation and for the very kind words. So we are going to talk about fascinating challenges of bluff body aerodynamics. Actually, all bluff body aerodynamics is a challenge. Here you see two design challenges, but these challenges are very much involved with bluff body aerodynamics. The role of bluff body aerodynamics is fundamental. You will see that these two challenges were faced in completely different ways and solved in completely different ways. This is a short outline. You may read it by yourself. Actually, I imagine that most of you are already very much familiar with all this topic. And I will start from the beginning. The very beginning is just the definition of aerodynamic and bluff bodies. And obviously, we cannot content ourselves with a definition based only on geometry. And by saying, for instance, that an aerodynamic body is elongated in the streamwise direction and the bluff body is not. This is obviously true, but this does not give all the story. It is better to classify bodies considering the features of the flow they produce when they are in a cross stream and the consequences of these features. Obviously, to do this, I must remind you, you all know what a boundary layer is, that it is produced by the no-slip condition at the wall. But the important thing is that if the Reynolds number is high enough, as is always the case in wind engineering, say, the thickness of boundary layer remains small, very small with respect to the length of the body, I would say. So this permits the application of Brown's boundary layer theory, whose main result, a fundamental result, is that the pressure at the edge of the boundary layer is the same acting on the wall. And this is fundamental, as we will see in a moment. However, you all know that if the curvature of the wall is excessive and producing an excessive adverse pressure increase, then you get boundary layer separation, and this produces this completely changes the physical and mathematical character of the flow, and you get totally different prediction procedures when the body has an attached or a separated boundary layer. So at last, we may define, classify our bodies in aerodynamic bodies as those for which boundary layer remains attached over the whole surface, and they produce thin and usually steady weights, and bluff bodies which give a more or less, which are characterized by a more or less premature separation of boundary layer from the surface and always give wide and generally unsteady weights. Here are examples of aerodynamic bodies, obviously from the aeronautical field, and here is an example from the animal kingdom. This is perhaps the most aerodynamic animal in the world. And these are examples of bluff bodies. And obviously, you see that there are no bodies which are always aerodynamic, because if an airfoil is at a sufficient angle of attack, it becomes a bluff body because boundary layer separates. And another example from the animal kingdom, actually, this is an example of, I would say, fluid body interaction, as you see here on the mane of the lion, and you see a very nice separation here. This is a recirculation, and here it's going up. So this definition has implications and consequences. The implication is that obviously the Reynolds number must be sufficiently high. And the other is that there are strict restrictions for a body to be aerodynamic. Not only it must be elongated, obviously, but it must have a sharp rear end to avoid separation of the boundary layer. And thus, obviously, you may think that this is a broad definition, and you may introduce a certain degree of bluffness, consider, for instance, the dimension of the wake or the extent on the surface with attached boundary layer and so on. This is very good. You may do that, but what is important really is what happens and what are the consequences of the presence of a separated wake. This is just to remind you of the definition of the load coefficients. Obviously, rho is density, v is velocity, s is a reference surface. Sorry. And now, drag of bluff bodies, this is the important point, is normally much higher than the drag of aerodynamic bodies having the same dimension, cross-flow dimension. And also the efficiency, I mean, the ratio between lift and drag for an aeronautical body is much higher than that may be produced by bluff body, especially because they have a high drag. But especially also bluff bodies are subjected to much higher unsteady loads due to the wake fluctuations. This is a famous comparison between the dimensions of an airfoil and a circular cylinder experiencing the same drag when moving at the same velocity. Here is the cylinder. You remember this is due to the fact that the drag coefficient of a cylinder is 15 to 20 times, depending on Reynolds number, higher than the drag coefficient of an airfoil. And we may interpret this difference in terms of perturbation produced by the motion of the bodies on the flow. And indeed, the work done on the fluid by the opposite of the drag force in a certain time interval is equal to the increase in total energy in the field. It means the increase in kinetic energy and internal energy to the dissipation. And obviously, in this case, so you understand that the drag is connected to this perturbation energy. And obviously, if you have a wake like this one of a circular cylinder, we will talk a little bit about vortex shedding. And obviously, you cannot produce all this kinetic energy and do not pay for it. You see that the kinetic energy produced by an aeronautic body is aerodynamic body is much less. And so now just a few slides with equations. We will deal with equations of incompressible flow, because in wind engineering, the velocity is sufficiently below the velocity of sound. I may say Mach number is below 1, always below 0.3. So we may assume density to be constant. And this produces this set of equations, which actually are not very easy. Actually, in incompressible flow analysis, the energy balance is uncoupled from the other two. But the most important one is the momentum balance, and this term is the nonlinear term, which makes this set of equations extremely difficult. Actually, there is no present proof of the existence of ionicity of a solution for generic boundary conditions. So this is a very, very difficult set of equations. And so what can we do? Is it possible to simplify the treatment? And especially, are there differences in the prediction of the loads for aerodynamic and bluff bodies? And this is the point. And there are indeed. But to show this, I must introduce vorticity. Vorticity is mathematically the curve of velocity, but physically it represents twice the angular velocity of an elementary volume of fluid. And so vorticity, where is vorticity? Vorticity is in the boundary layer. It is generated by the no-slip condition, and practically it remains confined in a thin boundary layer for an aerodynamic body and in the wake. Outside the wake and the boundary layer, the flow may be assumed to be irrotational. Now, the presence or not of vorticity has enormous consequences on the equations of motion, as we will see in a moment, and on the methods of evaluation of the loads caused by the body, on the body. In particular, you may see, and we'll see in a moment, that outside the boundary layer of an incompressible flow behaves as if it were non-viscous. And to just show this, I must manipulate a little bit the momentum balance equation, and you believe that all these vector identities are true. So I may write the nonlinear term in this way, and the Laplacian of velocity in this way, and I also assume body forces to be conservative. And so what I get is the most important equation for incompressible aerodynamics. In this equation, everything is contained, everything. And you see in a moment, first of all, obviously, if the curl of vorticity is 0, so you don't even need vorticity to be 0, but it to be constant, for instance, the viscous term vanishes in the momentum equation. So the momentum equation of incompressible flow of a viscous fluid coincides with the corresponding one on non-viscous fluid. So in all regions where curl of vorticity is 0, the fluid locally behaves as if it were non-viscous. And this is true because this term does not represent the viscous force acting on a surface of the fluid, but the resultant per unit volume of the viscous forces acting over an elementary volume of fluid. That these equations refer to the motion of elementary volumes of fluids. Sorry. And so the other consequence of that equation is that it shows what are the conditions for validity of Bernoulli's theorem. And you say that it is not necessary that the fluid be non-viscous for the validity of Bernoulli's theorem, as you find in an enormous number of books, but only that the motion be steady and rotational. Obviously, if the fluid were non-viscous, that would be sufficient, but in the world there are no non-viscous fluids, so that will be a problem. Now, what happens if vorticity is zero? Velocity may be expressed in terms of a potential, a scalar potential, and the continuity equation becomes Laplace equation for the scalar velocity, and then the velocity potential, and you obtain velocity, and then from Bernoulli's theorem you get pressures. Now, however, you may show that in presence of solid surfaces, you cannot have a completely irrotational flow. Nonetheless, it is possible that it be concentrated in limited regions, and this happens indeed for aerodynamic bodies, and is the origin of the simplified procedure evaluation of the loads for an aerodynamic body. Indeed, imagine you are an aeronautical engineer dealing with the prediction of the loads on a wing. So you have this real flow with small boundary layer, thin boundary layer and wake. And the first thing you do is just to squeeze the boundary layer to zero thickness. And you remember that the Prandtl result, that the pressure acting on the body, on the surface, is the same acting on the edge of the boundary layer. This is actually fundamental at this point. And then you may solve Laplace equation for potential, get the velocity, get the pressure distribution, the corresponding pressure distribution, use these to evaluate the boundary layer equations, to solve the boundary layer equations, obtain a first evaluation of drag and the thickness of the boundary layer of something that is relative of. This is actually the displacement. Singular is not very important. Then you get this thickness and you add it to the original body to evaluate the potential flow tangent to a new virtual body. Then you may get a second pressure distribution, a second evaluation of lift, drag, and thickness of boundary layer. You may iterate and obtain required accuracy as much as you want. This is fantastic. So you see that aeronautical engineers are very, very lucky because they can use this procedure. And actually, this procedure has been used for 1 century. And the airplanes were designed and the loads were predicted where obviously computers did not exist. So you get these nice pressure distributions, for instance, for different shapes of airfoils and angles of attack and so on. This is nice, but wind engineers are not that lucky because they have to deal with bluff bodies. And this simplified iterative procedure is not applicable for bluff bodies. And so what? And so why this is not? Because this is the point. The potential flow tangent to the body surface is no longer a first approximation of the actual pressure distribution, as was the case for aerodynamic bodies. Indeed, you see here a circular cylinder. This is the potential pressure distribution. This is the real for 2 different Reynolds numbers. So what you can do? You just have to use wind tunnel tests or nowadays numerical solutions. However, for the Reynolds numbers, which are typical of wind engineering, direct numerical solution, the equations of which you know is not feasible, and you must introduce simplified models and procedures. And even for a wind tunnel tests are complex, and then you may expect a certain degree of uncertainty. And indeed, this you can see from this very nice benchmark that was organized by ANIV some years ago, the flow around the rectangular 5-to-1 cylinder. So blind benchmark, there were no available reference data and were many researchers participating. So the aims were to assess the consistency of wind tunnel and computational results and to compare experiments and computations. And you see, this is what you may expect. It is the instantaneous flow. This is the mean flow. You see, the mean flow is characterized by this recirculation region. And this produces a pressure distribution of this type. I mean, this is the type of pressure distribution you may expect. These are pressure coefficients, actually, and this is a standard deviation. So you see, you get a maximum standard deviation, maximum fluctuation around the point where you have the closing of the recirculation, reattachment of the flow behind the recirculation region. This is what you expect, and this is what you get. You get in wind tunnel tests and numerical results, and you can see that you get a very, very large spread of the results. This is actually the statistics of this mean pressure distributions, and you see the scatter is very large, perhaps too large. And where does this scatter come? It comes from the uncertainty in the experiments, for instance, but which comes from the oncoming characteristics, coming flow characteristics like turbulence, homogeneity or non-homogeneity, misalignment between the flow and the model, the quality of the model, and so on and so on. And in computational fluid dynamics, the difference comes from different numerical schemes, different approaches, different discretization of the equations, which give rise to different topologies. And you see here, for instance, the result of a number of numerical outputs, and you see the difference in the topology of the flow, in the recirculation region. They are very different. So you obviously get very different results. How you cope with this? Well, you can cope with this with a, this is for the pressure fluctuation. You see that the scatter is even larger. So this causes uncertainty in the prediction of the unsteady lift forces. Now, you cope with this. This scatter comes from the effect of many parameters that influence both wind tunnel and numerical results. The classical engineering approach would be a deterministic one, in which you determine more or less, you imagine what are the intervals, the various parameters acting may have, and then you make a lot of numerical and wind tunnel tests to carry out them and to see the effect of these parameters. This is very expensive. This is very expensive in no terms. The other approach is a stochastic approach, which is a very new one, a rather new one, I would say, uncertainty quantification. And uncertainty quantification, in this analysis, the parametric uncertainties, the evaluation is carried out by using probabilistic methods, and the outputs are the stochastic mean value and the stochastic standard deviation of the values of the various quantities. And so what you get is a sort of response surface in the whole parameter space by using a few simulations, which, however, must be chosen and planned in a very smart way from both the mathematical and the physical points of view. And actually, this is a technique which is not that easy from the mathematical point of view. It's rather complex. Maria Vittoria Salvetti is an expert on this. And so this is where we stop a moment. And now we change subject. We go to vortex shedding. You probably know it. This is one of my favorite subjects on bluff body aerodynamics. This is an example of shedding, or alternate shedding of vortices, which happens for all. It's typical for all two-dimensional bluff bodies, but also for elongated bodies such as chimneys or skyscrapers, as you've seen. You know that von Karman studied it and theoretically derived the ratio of the longitudinal cross flow dimensions that is stable, and which is indeed very near the available observations. And you know the vortex shedding occurs with a frequency that is directly proportional to velocity and inversely proportional to the width of the body, and the coefficient of proportionality is the Struve number. And you see that Struve number is inversely proportional to the wake, which means that if a wake is wide, you get a low frequency. If the wake is not wide, a higher frequency. Then the important point here is that you may demonstrate that the kinetic energy associated with a couple of counter-rotating vortices is proportional to the square of the global vorticity that is present in their cores, and increases with the increasing of the mutual distance and with the decrease of the radius, which means that the more the two vortices are, two counter-rotating vortices are concentrated in small regions of space which are far apart, the higher is the kinetic energy associated, and this gives rise, obviously, to a high contribution to the mean drag. So, high vortex shedding, high drag. Obviously, vortex shedding also produces fluctuating cross flow and drag forces, and the frequency is the same of the vortex shedding frequency for the lift is twice for the drag. Obviously, the fluctuating cross-flow forces depend on the shape of the body, in particular on the dimension of the longitudinal stance of the body, which is inside the wake. So this body will give you a large lift force, this a small fluctuating force. Now, you may have, for instance, vortex shedding for more complex vortex shedding for a rectangular cylinder, because you have the shedding from the leading sharp leading edge, which interact with the shedding from the rear edge, and these vortices move. And also in this configuration, you may have fluctuating torsional moments, which are very, very obviously may be dangerous. And obviously, if the vortex shedding frequency is near to the natural frequency of the body, you may have a erratic response, which we will see in a moment is rather complex and nonlinear. Now, regular alternate vortex shedding may occur only if the separation line is rectilinear. This is very important in the spanwise direction. So if the separation line is wavy or irregular, the shedding of vorticity is also irregular. And so the energy content of the wake is much lower. So the less regular, I would say, the less regular is vortex shedding, the lower is the energy of the flow, and thus the drag of the body. And now, if this is the case, you may make the vortex shedding regular by introducing geometrical disturbances. And so, for instance, you get a reduction of, in this way, you may get a significant reduction, even say 40% reduction of the mean drag coefficient and of the oscillating forces. And thus you may hope, but that hopefully, but not necessarily say, you may avoid possible vortex-induced oscillations. Now, I change subject again, and I want to show you a few what I call non-obvious effects of the change of geometrical parameters. These are, again, very famous cases. One is the wind tunnel test carried out by this guy Morel in '78. Imagine, use an axisymmetrical body with a circular cross section, and which had a slanted base, sharp-edged, at different angles. It changed this angle from very low values, say 20 degrees to 90 degrees in 2 wind tunnels. And this is what it got. So you got that for very small angles, you had, say, a small drag coefficient, which increased dramatically by increasing the angle, up to a certain value at which you found a discontinuity, a sharp discontinuity of the load, and the drag became very much lower for high values of the slanted angle. And this is the effect on the half base on the pressure. These are negative pressures, so these are suctions increasing by increasing the angle of the slant, and then if the angle becomes too large, the pressure distribution becomes constant and much smaller. Where does this come from? This comes from the flow, obviously, the configuration of the flow, and from the presence and the rising of two concentrated vortices from the edge of the base. And for low values of the angle, you have these vortices which increase as the angle increases. They increase their strength. So increase their strength, increase drag. These are very much the same as the type of vortices which occur over a delta wing. at high angular attack in landing conditions, for instance. But if the angular attack is excessive, the vortices burst and awake with diffuse vorticities form. Thus, you see that the physical explanation of the data is that this continuity angle separates two very different types of flow. The first with concentrated vortices, which increase in strength as the angle increases, but the second one with the vorticity, the diffuse vorticity into wake, and thus a lower drag, a lower kinetic energy produced. This is very important, and you see this is dangerous. Say, imagine you had started making experiments from this angle, you reduce it and say, okay, it's not that important, so it will be a low drag. And actually this happened, because you see this phenomenon may also occur for car-like bodies, and you get, for instance, for this model, an enormous drag coefficient. Imagine normally nowadays drag coefficient around 0.3, sorry, for a car. And in the 70s, there were several cars that were this type of bodies, but then they learned a lesson. But actually, these vortices may be destroyed even by just putting a spoiler here. This is what you can see in many cars nowadays. Now, another case of discontinuities and no obvious effect. Interference. Interference is an extremely complex field in bluff body aerodynamics, and this is a classical test that was done. You have two rectangular cylinders separated a certain distance, and what you do is to increase this distance. And you see what happens to the loads, the drag in this case, acting on the upstream and the downstream cylinders. This is the result. And again, you see there is a certain distance at which you get a very sharp discontinuity. Actually, you see you may have two values at the same distance, and we will explain in a moment what this means. But what happens here? What is the reason? The reason is that for lower values of this distance, the shear layer detaching from the leading edge, the sharp leading edge of the upper cylinder, separates and then reattaches on the side of the downstream body, and you do not have vortex shedding here. And in this region, you actually have a more or less steel region with low pressures. Low pressures mean that the downstream cylinder is has a negative drag, so it gets a traction. This is well known actually. But what is the reason of this sharp discontinuity? The reason is that suddenly the vortex shedding starts to occur from the upstream cylinder, and this obviously causes a very high drag on the downstream cylinder, and also increases the fluctuating forces. Sorry. Now, you see that interference may give rise to a very complex flow configurations, and actually, you see, in this case, only tandem. The only cases were considered were tandem cylinder one behind the other and side-by-side cylinders, and you get very different configurations. For instance, first the body may act as a single body in the two cases. Then you get bistable flows. You see, for instance, here is a wide one, has a wide wake, the other is a narrow wake. But these two configurations may switch to the other one. So so this flow is bistable, which means that the same conditions you may get two different configurations depending on perturbations coming from upstream. You may understand this is quite dangerous, maybe quite dangerous. And then for higher distances, you have coupled vortex shedding. You can see this from these visualizations, and you see very well the situation with biased flow here. Sorry. The situation becomes much more difficult, much more complex if you have staggered signals. So you may get an enormous number of different configurations. A guy in Australia found something like 9 different possible configurations, producing forces in lateral direction and producing also possible instabilities, new instabilities due to interference. Here is an example of what I was saying about bistable flow. You get here two exactly at the same, in the same configurations, in the same configuration, you get two possible different flows, one with vortex shed and the other without. One point, very important point in interference, is that a body for which you for instance, you do not have cross flow mean forces, when in interference, cross flow forces act on that body. So that is may be very dangerous if you just think that a body behaves as if it were isolated when it is in interference with other bodies. The last part will be devoted to the aeroelastic phenomena, and you know very well this is the most famous example of a disastrous effect of aeroelasticity of bluff bodies. And this is a table in which you have different types of aeroelastic phenomena that may occur: buffeting, galloping, flutter, classical fluttering, vortex shedding, and what is the fundamental cause, a possible cause, and so on. First starts with the fundamental cause. I will say a few words only about galloping and vortex shedding. Galloping, obviously, the origin is the body oscillation. Vortex shedding is the unsteady separation, as we saw. And galloping, I won't go into the details at all. We just imagine you start with a body which with velocity in the x direction and which may move only in the y direction, and a possible movement in the downstream, for instance, direction gives rise to a positive angle of attack. You believe me that if you consider non-measurable variation of the cross-flow force coefficient with angle of attack, and then you find fluctuating y force in the cross-flow direction, which has this form. You see, it is proportional to velocity of fluctuation and to velocity. With this term here, which is the important one. So if your body belongs to a system of a single degree of freedom system, a certain mass, stiffness, and damping, and this is the equation of motion, you see that the aerodynamic force adds to the damping, you get a global damping, which has this form. And now, you imagine this is positive, always positive, the structural damping. May this become negative always? It must become necessary if the damping becomes negative. So the condition, the necessary condition for the global damping to become negative is that this term becomes negative. This is called Den-Hartog criterion. If this happens, then you get a critical velocity above which the damping becomes negative. So you have a very bad situation. How may this happen? Why bodies, for instance, aerodynamic bodies, this cannot happen because the derivative of CL respect to alpha for a aerodynamic body is very high, positive and high. So how you can get a negative force for a positive angle of attack? Because the boundary of the wake in the lower part has a higher convex curvature, which gives rise to high velocities, low pressures. These low pressures more or less act in this region. They are not the same, obviously, but all these regions have lower pressure than the upper region. So you get globally a downward force. Obviously, if the body is too long, then you get reattachment and you get a positive force. What are the type of bodies that may undergo galloping? For instance, square cylinders and rectangular cylinders, but not if they are too long. You see, it becomes positive, or if they are too short, you don't have enough surface for a lift to be produced. Now, what you do, you must avoid galloping. Obviously, you must avoid galloping, and note that galloping may occur in more than one degree of freedom. But if you block one of them, this does not avoid galloping in the other one. And now it should prevent it by, for instance, increasing damping, obviously, and increasing the natural frequency. See, the velocity is proportional to frequency and damping. And so also, obviously, you may modify the shape of the body, for instance, by rounding the corners or adding indentations. Now, vortex shedding. Vortex shedding response. Obviously, you may expect a response in the cross-flow direction when the frequency of vortex shedding given by the Struer relation, which is this one, is near to the natural frequency of the body. So this relation must be satisfied for the velocity, and the oscillations in the line when you have the double frequency. But in practice, most important are the cross-flow oscillations, so we will talk about that. Now, the point is that the oscillations due to vortex shedding are non-linear. I mean, this is a non-linear response, and this is the problem, because the forces causing the oscillation depend on the amplitude of oscillation they produce. So the first point is that, and this is a bad point, if the cylinder oscillates at frequency in an interval around the frequency given by the Struer relation, not exactly, but in an interval, the vortex shedding occurs at a frequency that is not that one, but is equal to the frequency of oscillation. So, for instance, to the natural frequency of the body. So you get what is called a synchronization or lock-in between the two frequencies. And within this interval, the cross-flow force increases with the amplitude of oscillation, and this is a bad thing, due to the rapid increase of the correlation of vortex shedding along the span of the cylinder and of the strength of the vortices. Fortunately enough, this does not increase indefinitely. There is the phenomenon is self-limiting, because significant changes in the vortex shedding pattern occur for amplitudes above, say, 1 diameter, above which it becomes a damping force. This is a typical response in terms of velocity. Actually, this is reduced velocity. You see, there is an interval of response for which the velocity, the shedding frequency is equal to the frequency of the natural frequency. So the shedding synchronizes to the natural frequency, and the oscillation amplitude is inversely proportional to this parameter, which is called the squared number, which is the product between the ratio between the mass, the per unit length of the body, and the mass per unit length of the fluid, times the damping, times the damping. Now, if this value, the value of this Scruton number is below a certain, say, 15, 10, 15, then you get very, very small, the oscillation, the response is very, very small. So you may practically, in all cases, disregard it. This can be achieved only in air and not in water. Actually, you are not normally concerned with water, but anyway. So what can you do to avoid or reduce vortex shedding oscillation? The first thing to do, obviously, is to increase the first natural frequency in the design stage so that the maximum velocity of the flow, the wind, is below this value. And this is very nice, but it's not easy, because if you have a large structure, it's increasing the frequency is not, the natural frequency is not that easy. So what you can do is to increase the Scruton number, and try to do this by increasing damping, which is always good, so that the amplitudes that you get are not dangerous, not for fatigue, nor for the functioning of the body. Or you may use increasing damping, for instance, by adding devices dissipating energy, such as tuned bus damper, which is much used in skyscrapers. But you may also change the shape by adding, for instance, fins like these very famous strakes. You find these in many chimneys, especially in Northern Europe. And this is very efficient because obviously it avoids completely the correlation, the vortex shedding. And so you have no problem about vortex shedding response. Obviously, unfortunately, the drag increases a lot. It practically doubles. So you have also increased static deflection, which is not a problem, but also increased buffeting response. Now, that's all. I mean, we go to our skyscrapers. You remember the skyscraper? We started with a skyscraper. And this is the famous Taipei 101. And its shape, okay, it represents what they say iconic Asian symbols, but has an almost constant square cross section. Actually, it's not exactly constant, but vortex shedding is very treacherous. So you see, this is not the change, the variation in cross section is not enough to avoid a vortex shedding at a mean, say, frequency given by the mean diameter, the mean shape. Also, there are indentations which are very good for galloping, but all this constant section, 500-meter tall body is obviously subjected to possible oscillations due to wind, very significant oscillations, and to avoid them, they had to introduce a large tuned mass damper, which are actually a 660-ton pendulum, which is now, it works very well. It works extremely well. It moves indeed. And it has become actually a touristic attraction. And then the other one, I mean, Dubai Burj Khalifa, which you know is the tallest skyscraper in the world. And this skyscraper did not need a damper, any tuned mass damper, any added devices. Why is this so? Because its shape is completely changing. It is not only tapered, which is a good thing, but its shape, you see the shape of the various cross sections continuously change along the height. And so this completely uncorrelates not only vortex shedding, but all the aerodynamic forces. So even for buffeting, this is very much useful. So this is a very nice solution. So you see two completely different ways of solving the problem, and depending obviously on the what you can do, if you can or cannot change the shape of the body. Now, some open points, which I think are, we end with these, some open points. We start with the interaction between vortex-induced and galloping oscillation. All the treatment, especially of galloping, imply that the reduced velocity for galloping is sufficiently higher than the ratio of velocities for vortex shedding excitation, vortex shedding response. Otherwise, our treatment does not is not valid. This is usually true for except for low scruton numbers, but actually there may occur problems, for instance, for bodies of particular shape, like reticular cylinders with a 1.5 ratio between the sides, as Manini has shown very recently, and the group of Florence has shown very recently. So this is a problem, because what they found is that you get galloping starting at the same velocity at which you expect the response to vortex shedding. That is a very difficult condition to predict. That's the point. You cannot easily predict this. Now, another point is obviously what you saw, the poor agreement between experiments and numerical simulations. So you must carry out a deeper critical analysis of all the factors which influence the scatter of the results within experiments and simulations and between the two approaches. What we need from a numerical point of view is improved numerical approaches for separated flows at high Reynolds numbers, and with the complex dynamics of vorticity. Now, as I also told you, interference between bluff bodies. I think that the present knowledge about the effects of interference is very, very far from satisfactory. The problem is we need dedicated investigation, at least for the most usual shapes and configurations, but they are quite expensive, as you may imagine. So this is a point that should be faced deeply. And the other one, and the one Genoa is involved now, is the prediction of aerodynamic loads in unsteady condition, because it is important for loads in thunderstorms, in which you may have significant accelerations and decelerations of the flow. So you have loads linked to acceleration. And remember, these loads linked to acceleration are not the same if the body is accelerating or the flow is accelerating. And this is one thing that not everybody remembers. And what we have to do is to understand which are the limits of a quasi-steady approach, which means, is it possible to use the force coefficient we obtain for steady flow in wind tunnels or numerical simulations? So what we need are dedicated experimental facilities and numerical simulations. And just to end, I want to show you a slide with some what I call philosophical conclusions on bluff aerodynamics. I wrote these words some more than 20 years ago, but I think they are still valid, and we may read them together. What I say is that the investigation should not be a mere collection of data on the variation of the loads as a function of the many geometrical and fluid dynamic parameters that affect the flow, but inversely, conversely, we need to connect what we find, the observed trends, with the characteristics of the flow, with the physics of the flow. Only if the physical mechanism are understood may we devise means for changing the flow in a favorable way. So what I say is that only the comprehension of the physics may allow us not only to predict which laws and phenomena may be expected in a certain situation, which is good actually, but also to design new shapes and configurations in such a way that certain design characteristics of the running field be obtained. But now, when I was young, as you are supposed to be, this was very difficult indeed. But nowadays, you may use synergetically the wind tunnels and numerical simulations. This is extremely important because numerical simulations, even if you have a simulation that does not give you good or perfect quantitative results, normally they give you good qualitative results, which means that you find a phenomenon, a physical phenomenon, if it is there. Just as an example, imagine you do not know that voltage shedding exists, but you find fluctuations in wind tunnels on the loads. But then even the worst code for a simulation, flow simulation, will give you voltage shedding. Perhaps it will be the wrong voltage, and certainly will be the wrong voltage shedding, wrong strength of the vortices, distances, true number, and loads. But the fact that the voltage shedding is there, you will realize that that phenomenon is there, and perhaps you couldn't understand that from the wind tunnel. Or also, we also saw concentrated vorticity. Also, in this case, perhaps you won't get the right condition at which you get a discontinuity. Okay, but the existence of the phenomenon may be found from American simulation. So you are luckier in this, and you must work on that. Always find the connection between the physics and the results. So this is really the end. So thank you very much for your attention. That's all.